PhD from Caltech, then did postdoctoral fellowship at Berkeley before joining University of Pennsylvania. He's a recipient of numerous awards, including NSF Career, George Axelby Outstanding Paper Award of IEEE Transactions on Automatic Control, Google AI Research Award, and many, many others. He's supervising a large lab working at the intersection of machine learning and control. And with that, it's all yours, Nick. Go ahead and get started.
All right. Thank you, Naira, for the really kind introduction. Thank you for inviting me to give this talk in this seminar series. Thank you, everybody, for joining today. Happy Halloween. I'm really excited today to tell you a little bit about some work that we've been doing in my group, thinking about machine learning for the physical world, and in particular, trying to maybe suss out and understand what's different about machine learning over data generated by physical systems in contrast to more classical machine learning approaches, things like natural language processing, image classification, and things like that. This is going to be a little bit more of a theory talk than an applied talk. And these days, I feel as though you kind of actually have to justify the role of theory in the current landscape. And so I want to start with maybe a little bit of motivation as to why theory might still be interesting in this world of large language models and things like that. We've all lived through in the past 4 or 5 years this foundation model, this large language model revolution. We've seen it first for language and then kind of proceeding to vision, this recipe of taking internet scale data sets, feeding them into massive models, using massive amounts of compute to then generate models that are capable of really astonishing generalization. In addition to this revolution, we've also seen somewhat of an evolution moving from more traditional machine learning domains, things like language and vision, to embodied action, embodied AI, systems that interact with the physical world. In this context, one interesting question that we might want to think about is whether this recipe of internet-scale data and large models can and or should be applied in this context. To maybe try to get a better sense of what are the challenges, I've got this little kind of maybe silly cartoon here that illustrates the difference between, say, training a large language model and these so-called robotics foundation models. If I want to train a large language model, I really, I have access to this huge amount of data on the internet that I can easily scrape and kind of transmit into my training algorithm. If I contrast this to something like robotics, where the data that I'm going to be able to collect is coming at a relative drip, 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 because I have to do this through expensive teleoperation or demonstrations, this leads to this Ken Goldberg has this really nice position piece where he kind of defines this robot data gap. Then, culminating this highlight that the difference in the amount of data that was used to train, say, a state-of-the-art robotic foundation model like Pi0 from Physical Intelligence, relative to a kind of state-of-the-art open source language model. And the difference in terms of the amount of data here is on the order of 5 orders of magnitude. And so this is kind of this really significant bottleneck.
I didn't know if any of that discussion had happened. So I'll continue to work that.
Sorry, someone's not muted, but I'll keep going here. So yeah, you have this very significant data gap in terms of the amount of data available. And this, in some sense, brings us to a little bit of a crossroads if we want to think about the path forward in the context of embodied artificial intelligence. On the one hand, we can pursue this more aggressive data collection perspective and try to actually build up an internet of robot data. And folks are indeed pursuing this direction, and they're doing some really interesting work in terms of scaling up more, realistic simulations, extracting behavioral and demonstrations from, say, video, developing novel hardware to facilitate the collection of data demonstrations. That's one path, very worthwhile and interesting. Complementary to that, and which will be a little bit more the focus of today's talk, is the idea that maybe for embodied AI, we're just going to have to settle upon the fact that we're going to have to be able to do more with less. right? And an indication that maybe this is something that we can do is that despite this very significant robot gap, we are seeing really impressive progress. Things like models from TRI or physical intelligence are doing really, really interesting things. So part of today's talk is going to be trying to reverse engineer some of the phenomenology at play in these systems to understand why we're able to make really impressive progress despite this lack of internet scale data for robotics. Then, once we've kind of performed this reverse engineering process, maybe we can try to extract out those lessons and use them to forward engineer more efficient learning algorithms for machine learning for the physical world. So really, these two questions are going to be the framework for today's talk. Now, so far, I've really been talking in the abstract. So before diving into the technical meat of the talk, I would like to maybe just ground our discussion in a particular example of a large model for robotics. I'm going to use the TRI large behavior model, not because it's my favorite or anything, but rather because in terms of the documentation and the papers and the blog posts, they actually give you a really nice insight in terms of a lot of the nitty-gritty details behind the scene. So how does this large behavior model's training process go? Initially, they collect a large, what's called pre-training data set, and this consists of on the order of a few dozen demonstrations for a whole bunch of different tasks. And you're going to do this across a lot of varied tasks. Then you're going to feed those different demonstrations into this very complicated model, which they call it, which is this kind of diffusion-based transformer. And they'll train this model on this pre-training task. What they've seen in practice is that this large pre-training data set, it can actually be fit and kind of you can do a really good job on this pre-training data set. But what's really even more interesting is that then suppose that you have a couple of new tasks that you're interested in, say attaching a spoke to a bike or coring an apple. It turns out that if you take this pre-trained model and then just give it a small number of demonstrations of each of these very complicated tasks on the order of a dozen, the model will actually learn to do them very quickly and do them very well. Right, so the promise here is the idea that I can train one policy on a small number of demonstrations from many tasks to quickly learn how to perform well on new tasks. Now, to the credit of TRI, they also make very clear that while this is a very conceptually appealing framework, there's a lot of engineering tricks that have to go on underneath the hood to make this whole recipe work. So some things that they highlight in their blog post is the fact that in addition to needing diverse data across tasks, even within tasks, you need a diversity of data. You need to show, for example, recovery behavior. You need to show the robot how to recover from failures. For example, if it drops a knife, you need to show how to pick it up. They also did a really kind of extensive ablation on all the different pieces of this diffusion transformer model here, and they really highlight the need for this rich policy parameterization. When they actually deploy this model on the robot to make it act, they do this really interesting mix of receding horizon control, which I think is a familiar technique to all of us, and this other newer technique that's emerged in the robot learning community called action chunking. We'll talk more about action chunking in a little bit, but for now, you could just think of this as purposefully operating an open loop longer than you need to. And then finally, they really emphasize the importance of having a good layered control architecture and doing this learning approach at the appropriate level. In this context, they're going to operate at this mid-level of position and orientation commands and let lower level controllers translate this to torque and code and joint commands. Okay, so a lot of moving pieces here, right? And so one thing that we're going to try to do today, at least in some aspects, is to try to demystify why these different kind of components of the recipe are needed, and then understand how this demystification can then inform practice. Our guiding principle throughout today is going to be this idea that is, very obvious, but it's worth stating, which is even though physical data is scarce and it's expensive to compute and it's difficult to get our hands on, it has a ton of structure. And so our goal is going to be to understand this structure and how to use it to make learning better, right? And what better means will depend on the context. I'm going to try to frame today's talk around a traditional robot learning pipeline. starting from system design, how do I build my system, to policy parameterization, to data collection, to the ultimate training of my policy. Hidden in this discussion will also be what happens when we deploy the policy, so don't worry, we'll also talk about that. Now, for each of these pieces, before we dive into the meat, I'd like to highlight maybe what are some of the challenges that arise in this context, in the context of physical machine learning, relative to traditional machine learning in, say, the context of image classification. So first of all, if we think about building our physical systems, building our robots, something that's unique to machine learning in the physical world is that the systems that we build are indeed the systems that generate our data. So we have a lot more insight and control over the data generating process in this context. Now, moving on from this context, from the system design step, if we think about parameterization and data collection, we're going to recognize that when I learn a policy, ultimately I have to deploy this learned component in closed loop. And so I can use this to shape the data that I see at test time, right? So another way of thinking about this is I get to control what my test time data distribution looks like. Again, very different from, say, traditional covariate shift questions that arise in the machine learning setting. And so we'll see how the role of stability, in particular in the context of imitation learning case studies, can inform some of these tricks that we saw on the previous slide. And then finally, last but not least, if we think about training, this really kind of key feature that we're going to need to try to address in this context is the idea that we have access to not large data for robotics, but rather thin data. And by thin data, I mean that I'll have a little bit of data for a lot of very different, say, robotic embodiments and or tasks. And we'll see in this context that it's essential that we adapt our training algorithms to the statistical properties of our data. And of course, these statistical properties will be very much related to the design decisions that we made in the previous two steps. Now, as much as I would love to talk about everything today, this would take a lot longer than an hour. And so I am not going to discuss the first step of system design, mostly in part because this is related to work on fundamental limits of learning and control. And this is something that I've talked about ad nauseum in a lot of my other talks. If you're interested to learn about that, please let me know. I love this material, but I just don't have the time to talk about it today. So what we're going to start today's talk with is discussing this first central piece here. And in particular, we're going to start with focusing on the parameterization question. How should I parameterize my policy to kind of account for what the behavior of my system will look like in closed loop? This next body of work, I just want to emphasize, is mostly led by my student Thomas at Penn. He is graduating and is going to be looking for a postdoc. He's amazing, so please reach out to him if you have positions. This is also done in collaboration with Dan Frommer, who was an undergrad with me at Penn and then moved on to MIT and is now working with Ali Jababai, as well as the incredible Max Zimchowitz, who just started a position as an assistant professor at CMU. And so the questions that I want to discuss, I want to frame them in the context of a very important case study, which is imitation learning in continuous state action spaces. This is very much the underlying or enabling technology behind, for example, this large behavior model that I showed you earlier, where we get expert demonstrations from a teleoperator, and then we try to reproduce those in a learned policy. So let's try to formalize this question a little bit more. Let me also just pause really quickly and just say that I forgot to mention this, but if you're in the audience and you have a question, don't be shy. Feel free to unmute yourself, interrupt me. I'm happy to take questions as we go. Okay, good. So we're going to talk about this imitation learning problem. What is imitation learning? The idea here is that I have some expert policy that I like. This could be a human. This could be, say, a computationally expensive controller like a nonlinear model predictive controller, or ILQR, that induces a performance that I'm happy with. Now, the problem is that for whatever reason, this policy is not something that I can feasibly deploy on the system that I care about. If it's a human, well, humans don't scale well. If it's something computationally heavy, maybe I want to deploy this on a compute constrained platform. So the idea would be that I'm going to take this expert policy and I'm going to execute it on my system to collect a data set. This data set, you can think of it as labeled pairs of a state and the action that my expert policy would take on that state. For this part of the talk, I'm going to use blue to highlight the expert data. We're going to feed this into a supervised learning problem, which I'm going to just conceptually capture in terms of this imitation loss, where we're trying to fit a red policy pi hat. I'm going to use red for our test or learn policy on the data set D generated by my expert. An example of how you would do this would be to minimize some norm in terms of the distance of their actions on the expert data set. This will then produce a policy pi hat, which again, I want to emphasize is a function of the data collection from my expert. And you'll notice that the picture, maybe hopefully you can see this, the picture of our little Einstein expert here on the right is kind of a blurred version of the one on the left. And this is to emphasize that we're going to do our best to imitate our expert, but it's going to introduce some small errors inevitably because we're learning it from a finite amount of data. And then we're going to take this policy and deploy it on the system, and this will induce a corresponding performance. Now, the fundamental question of imitation learning is whether we can guarantee that the performance induced by my learned policy relative to the performance of my expert is small if my imitation loss is small. Right? And so I would like just to unpack this a little bit to maybe highlight why this isn't an obvious question and to also highlight what could potentially go wrong. So first of all, let's just understand what having a low imitation loss actually gives us. So what I plotted for you here is a cartoon picture of, say, an expert trajectory. So I start at x1 star, I take the optimal policy pi star, apply it to x1 star, and this moves me on along my expert trajectory. Now, what a low imitation loss tells me is that if you drop me into any one of these expert states, x1 star, x2 star, x3 star, etc., and then I apply pi hat to it, it'll give me an action that is not too far off from what the expert would have done. Now, this seems like an intuitive thing, and hopefully this will lead to some decent behavior. But here's kind of the catch, right? Which is the performance of my policy is not exactly the imitation loss, because now I'm actually deploying my policy in closed loop. So while I start at x1 star in this deploy, if let's say I'm starting at the same position, where I end up with after my first action is a little bit different because I've induced some error. Now I take an action from this red state instead of the blue state. This induces a little bit more error. This compounding error kicks me out even farther, which results in a bigger error and ultimately kind of this failure, right? This is the well-recognized, well-understood problem of compounding error in imitation learning. Now, in discrete state and action spaces, you can show that if you do things properly, this compounding error is actually fairly benign. In some work by Max and Dan, as well along with Ali at MIT, they showed that in the continuous action space setting, this is actually a much more fundamental problem. So for example, here is a hardness result that's going to motivate a little bit of what we're going to talk about next. They show that there are deterministic smooth systems that are open loop stable and that have stable expert closed loops, right? So this is as idealized a setting as you could hope for. And for those of you who are wondering what I mean by stable, we'll explain that very precisely in a few slides. But for now, you can just think of this as an extremely strong version of stability. Under this idealized settings, there are problems for which I have an exponential difference between my performance gap and my imitation loss. My performance gap will be exponentially larger in the horizon of my task than my imitation loss. And not only that, this will be true for any smooth Markovian policy pi hat that uses only the expert data for training. Right? So this is a very strong negative result. And it tells us that even in this idealized setting of an open loop stable system with a stable expert closed loop, we need to either change the parameterization of our policy, or we need to change how we collect our data in order to overcome this hardness result. In this setting, we're going to start by thinking about how we should parameterize our policy. We're going to ask the question, how should I parameterize my policy to harness the underlying system stability, right? I'm assuming an open loop stable system. I should be able to take advantage of that some way. What I want to start with is an experiment that we ran in simulation that is, at first glance, insanely counterintuitive. So here's the setup. We're doing this tool hang task in the RoboMimic suite. We have an expert, which is some diffusion policy that was trained via reinforcement learning. that has a 72% success rate. So you should think of that as kind of the baseline that we're trying to reach. And what I'm showing you here are the rollouts of the same policy, but deployed in different fashions. So this policy predicts 16 actions in the future. And in the center video, it is being deployed in receding horizon control, which means it plays one action, remeasures, repredicts, plays one action, etc. This is our familiar receding horizon control approach that we know and love as control theorists. On the right, what I showed you is receding horizon control plus action chunking, where I purposefully play 8 actions in open loop before remeasuring and recomputing, right? And so I don't know if you were able to tell because these videos are a little strange, but the one on the right actually did a lot better than the one in the middle. And so if we zoom out and kind of look at the success rate versus the evaluation chunk length, this kind of the amount of time that we spend in open loop, for different prediction horizons, we see a really striking and, again, very confusing phenomenon. The way to read this chart is on the left is the success rate of just receding horizon control operating at 20 Hertz. And you'll notice that there's a sweet spot in the middle here where we purposefully force our system to act in open loop for approximately 1/3 of a second. And across all these different prediction horizon lengths, this leads to an improved performance in our system. And so when I first saw this, I was extremely confused. And so what we'd like to try to understand here is what on earth is happening. Why is acting in open loop on purpose the right thing to do? And so our starting point for trying to understand this is to formalize a notion of stability for the system that will maybe allow us to reason about what's going on. And so I apologize for the math here, but I'm going to give you some pictures to kind of associate with this. We're going to say that a nonlinear system with state X and control input U is this very mouthful of a word, C row exponential incremental input to state stable. For the rest of the talk, I'm just going to call this stable, but I really mean this more complicated expression. If the following holds for all initial conditions, blue X and red X, and input sequences in blue and U, you can think of these as 2 rollouts of my system happening in parallel. What I need to be able to do is instance-wise in time bound the deviation between these 2 trajectories in terms of a component that characterizes how quickly we forget the past, the difference in initial conditions, and our robustness to pokes, to differences in control actions. And so kind of a main feature of this very strong notion of stability is that we're exponentially forgetting the past, and we are also kind of, in some sense, exponentially or linearly robust to pokes of the system. We'll also say that a policy is stable in this sense if it induces a closed loop that satisfies these properties. If there's one thing that I'd like you to take away from this is this notion of stability captures linear-like or exponential stability, not towards a point, but between 2 different trajectories. Really, what we're going to want to do today is reason about stability in trajectory space. So this is a very natural notion of stability to consider. And so to start, we're going to assume, in some sense, the best case scenario. My open loop system is going to be stable in this sense. My expert system will also induce a stable closed loop in the same sense, and they're both going to have the same stability radius, or stability parameters, and I'm going to assume that everything is Lipschitz and smooth and beautiful. Even in this context, our hardness results still apply, right? So if I'm not going to change my data collection, this means that I'm going to need a richer policy class than just a Markovian pi hat of x spits out my action. So what kind of policy class might we consider? Inspired by the empirical results that I showed you earlier, I'm going to propose this class of policies called L-chunked policies. The intuitive idea here is these are policies that measure the state and then play L actions in open loop before remeasuring the state and then rinse and repeat. We're going to use a particularly convenient theoretical construction for this, where each policy pi hat will imagine some virtual dynamics f hat to kind of generate this forward rollout of L actions. Although I will just say this is really more of a theoretical construct that's useful, not something that's necessarily fundamental to the approach. And so here's a really interesting theorem that we're able to show, which is that if I have this pi hat f hat pair, that believes that it is stable. So I have a pi hat that believes that it is stable in the same way that the open loop stable system is. Then if I play a chunked version of that policy, I can guarantee that it will also induce a stable closed loop as long as the horizon is long enough. Now, this seems a little bit mysterious, and I'm going to give you some pictures and some intuition as to why this might be true. Now, the key idea here is that by doing this action, what's called action chunking, and this is, again, something that's somewhat standard in robot learning, we're harnessing the underlying stability of my system. So if I think about this in the context of, let's say, regulating to the origin, then this basically says that as I move forward in my chunks, because I think my system is stable, I'm going to be applying less and less control magnitude. So for a long enough chunk window, I'm just kind of limiting the ability of my policy to destabilize my already open loop stable system. Another way of thinking about this, and I really like this interpretation, is that rather than trying to parameterize a feedback policy to stabilize my system, I don't need to do that because my system's already stable. Instead, I'm learning basically an open loop forcing function over this window L. So my policy is learning guiding pokes, telling my system where to go, rather than a feedback policy. So just in terms of a picture to maybe explain what's going on, I want to look at a very simple cartoon as to why this might be a believable result. So let's consider just a very simple system with a scalar state. And let's consider a very well-behaved expert system. So my system is just this stable linear system. Every time step, if I don't apply a control action, my state is halved. Right, so this is converging to zero exponentially quickly. And my expert policy is doing nothing, right? So this is a very benign system. So my expert system will just, if I roll it out from a given state, this is what's going to happen. Now let's consider a admittedly bad candidate function, candidate policy pi and dynamics pair pi hat and f hat, where my policy thinks that dynamics have a switch sign. So rather than being 0.5x, it's negative 0.5x. And for whatever reason, I've learned the wrong policy pi hat. But you'll notice that interestingly, the closed loop induced by pi hat is the same as the expert closed loop. Nevertheless, this can still get us into some trouble. Right? What I'm drawing here is kind of the internal model that our learn policy has of the world. So when it looks at the first state, it just measures its state and determines what it should do. This ends up being in the wrong direction because its model is wrong. It then re-measures, goes again in the wrong direction. And kind of the takeaway here is that even a simple policy like this, if I put it in feedback, it can destabilize my system. Now let's contrast this to taking the same policy and deploying it in a chunked fashion. So I've kind of highlighted these bigger marks here along the time axis to highlight that we're doing a window of 3. Now, when I start at this first point, my chunked model is now thinking about these 3 next time steps. And so what happens is I initially go in the wrong direction, but eventually the underlying stability of my system overcomes my error. And then we can do this again. Again, I have this forward-looking plan, and I take these steps that initially go in the wrong direction, but stability eventually takes over. And so the idea here, again, is that my chunking harnesses the inherent stability of my system and acts more as a guiding function than as a feedback controller. It turns out this is really the missing piece to be able to ensure in the open loop stable setting that we can ensure that our imitation loss is not indicative of our performance gap. Right, so under the assumption that we're deploying this chunk policy with the appropriate horizon, we can guarantee these nice behaviors. And the key idea, again, is just that I'm ensuring that the deployed policy is also stable, and so it prevents these compounding errors from happening. So if we go back to our experiment, if we want to kind of understand as to what's happening here, the message is that the reason that these chunk lengths are actually beneficial is that we're actually harnessing the inherent stability of our system. So where is this inherent stability coming from? Well, it's because we're doing this at the position and pose command level. This is at that level, my system is inherently stable, and in fact, it's even fully actuated. right? And so what we want to learn is a guiding function through imitation learning rather than a feedback policy. So if we kind of zoom back out now and look at this picture from the TRI large behavior model, this part of the talk gives us a little bit of information as to some of the pieces of the secret sauce. In particular, it tells us a little bit about why we need a rich policy parameterization. We need to move away from Markovian policies if we want to harness this mid-level stability. Similarly, this mixture of receding horizon control and action chunking applied at the right level of our layered control architecture is really what's allowing us to harness the built-in stability that comes from lower level model-based control. Okay, good. So we've talked about model parameterization in the context of deploying learned components in closed loop, but we did this in a very idealized setting where our open loop system was in fact stable. What I want to talk about now is how we can, in fact, even overcome the problem of an open loop unstable system if we're also clever about how we collect our data. So I want to go back to this slide here where I was kind of illustrating the challenges associated with imitation learning, even in this idealized setting. Now I'm going to change the hardness result at the bottom. Again, this is work from Max, Dan, and Ali that says that if my system is now open loop unstable, but I again still have a stable expert closed loop, I have this very challenging hardness result of this exponential compounding error issue. But now this is true for any policy pi hat trained using only expert data. So in this context, something like action chunking or more clever policy parameterization won't save us. We're going to have to change how we collect our data. And so that's what I would like to talk about briefly in the next few slides. So for this problem, for this part of the talk, our problem setup is that we have an open loop unstable system. But we're going to assume still some nice properties. So our expert policy and our open loop dynamics, we're going to assume are S smooth. Just as a reminder, when I say something is S smooth, I mean that the gradients of these functions are S Lipschitz. We're going to again assume our expert system is stable, and we're going to assume that all the possible policies that I can learn from my policy class are Lipschitz and smooth as well. I want to emphasize that these hardness results still apply, and we're going to need to think about how to change our data collection process. So what we're going to talk about next is how should I augment my training data to ensure that the learned policy is stable and performs well. Our starting point for guiding how we should collect our data is this result that we have from a prior work on imitation learning. And I want to just parse this result for you a little bit and then explain to you how it's going to inform our data collection strategy. So the condition of this statement here is saying that if I can ensure that the policy error between pi hat, my learned policy, and the expert policy pi star is small, and small means in some sense matched to the robustness of my expert system, and I can ensure that this is true not just on my expert data, but on an epsilon tube around that expert data, then I can ensure that that epsilon tube is in fact invariant under the errors between my two policies. So the idea here is that the underlying robustness of my expert makes sure that we're going to start at the same point. We're going to make an error that's at most kind of the inverse of stability times epsilon. The inherent robustness of my stability of my system will attenuate that and keep me within this epsilon tube. And as I proceed forward, this matching between the error that I make and the robustness of my system keeps me in this tube. Right, so this is important because if we're able to find a policy that satisfies this condition, then we've essentially guaranteed that we don't have compounding error. We are staying within an epsilon tube around our expert trajectory. Now, of course, the question then is, how do I find a learned policy that satisfies the above? I can't just drop this min-max type problem into my training algorithm. For the one part, it assumes that I can, query my expert policy on this tube around the data that it generated. Good luck asking a human, for example, to do this. So our idea is to take this expression and take a Taylor series expansion of it around our expert data. Right, so what I have for you on the slide is exactly kind of the inequality that's induced by taking a Taylor series. And the key observation is that we can ensure that the property that my policy error is small enough on this tube holds if these two terms are small enough, as well as epsilon being small enough. And a key feature of this is that these terms that I've highlighted in blue here are evaluated on my expert data. So this is something that I nominally can push down at training time. Now, this term that I've highlighted in green, this is exactly what we're minimizing when we're minimizing our imitation loss. So the question then becomes, how do I make this Jacobian error term small? Now, in previous work, we actually just assumed that we could get access to this Jacobian term and minimize it directly in training. This works in some contexts, but it was somewhat of an unrealistic assumption. So what we've been able to do is show that, in fact, you don't need to directly measure the Jacobian to make this error small. And our key idea here is to exploit smoothness of our system through data augmentation. We propose a two-step recipe where half of the data we collect as usual, we play our expert and we return our expert data set. And the other half of the data we collect, we noise the input. So we add some excitatory signal into the control action that we're playing. Importantly, though, we return clean labels. So we're still fitting on the clean actions that our expert policy would take. We're just inducing some spread in the data that we collect on this noise trajectory. What we're able to show is that, under suitable assumptions of controllability, if we tune our parameters correctly, we can, on the one hand, ensure that our Jacobian error is small, if our imitation loss is small on both the clean and noise data set. And we can then translate this using the results that I showed you on the previous slide into a result that guarantees that our imitation loss averaged across clean and noise data is in fact an upper bound on the performance gap of our system. To give you just a little bit of intuition as to why this might be true, there's this really nice picture that Dan put together, which shows on the left what happens if I train only on expert demonstrations for an unstable system. And the idea here is that as soon as I move away from expert data, I don't know what to do. I don't know how to stabilize myself back to it. In contrast, if I used only noised data, then I'm not actually getting true expert behavior. And so I'm going to exhibit jitter because I've induced this distribution shift even in the training data. However, if we combine things in the right way, you're able to get the best of both worlds. So for example, if I were to apply this to, let's say, a half cheetah environment where our expert is some reinforcement learning trained algorithm, if I apply just vanilla behavior cloning, just matching the policies to each other, you see this red curve fails quite miserably, and that's because it can't recover from errors. In contrast, suppose I tried to noise my data, but I trained on noisy labels instead of clean labels. This also leads to problems because now we're fitting to a noisy policy rather than the true policy. In contrast, if you take our approach, we use a mixture of clean labels, of clean trajectories, and those with noised inputs but clean labels, we're able to approach the expert very quickly with just 40 total training trajectories. So if we zoom back out and think about how these ideas relate to what's going on in the TRI large behavior model, this does give us a little bit of insight as to why we need a diversity of data even within tasks, right? In particular, this idea of including recovery behavior. What we just showed on the previous slide is that, at least in the context of continuous imitation learning, the data augmentation teaches local recovery behavior by ensuring that the Jacobians match. Okay, so that concludes our kind of discussion of the role of stability in imitation learning and how this informs both how we should parameterize our policies and how we should collect data. What I want to spend the last 10 or so minutes, 10, 15 minutes of the talk on is this idea of training, of the appropriate way to train our policies or our models so that they generalize well, not just within the training data, but across tasks. This following set of work is again led by my student Thomas in collaboration with Hamed student Birad and Leo and James at Columbia. So the motivation for this part of the talk is really going to be this idea of feature learning and transfer learning. Right, so one of the key enabling technologies, or the key enabling phenomena that allow you to train a policy first on a large number of diverse demos and allow it to quickly adapt and learn how to perform a new task is the assumption that there's some underlying shared structure across all of these tasks. Now, what feature learning tries to do is extract out these shared representations or shared features from the pre-training data to make fine-tuning on new tasks a lot easier. So what I'd like to propose next is a stylized model that might allow us to study that question a little bit. So we're going to talk about this idea of multitask and transfer learning, and this typically proceeds in two phases. There's phase one, which is called the pre-training phase, where you're trying to learn a shared representation. We're going to assume that each task is defined by a task head and a shared representation. So the cartoon that you should have in your mind is that I'm getting this pre-training data set. Each of these different colors here you could think of as corresponding to one of the different tasks that was used for pre-training. So let's say one is cutting, one is stirring, one is coring an apple, etc. We're going to feed all of these into a shared rich representation. You can think of this as this kind of big, massive transformer trunk of my model. And then I'm going to feed this into task-specific linear heads. So I'm going to assume a shared representation in this stylized model. The only thing that adapts to each task is the linear head of my model. And these will then be kind of tuned to task-specific losses. Now, the idea here is I'm going to get a lot of this pre-training data set. It's going to be very large, and it'll allow me to learn a good shared representation. And then in phase two, I'm going to adapt to a new task by transferring over a frozen version of this shared representation. And then, even though I only have access to a small data set for my fine-tuning task, well, I don't have to learn this new shared representation. It's frozen. So I feed it through. This gives me an embedding that I then feed into my target task and train on my target task loss. And the hope here is that because I only have to learn this target task head in the adaptation phase, then this should be more data efficient. So let's take this kind of cartoon picture and specialize it to a linear imitation learning setting. So suppose that my experts are characterized in terms of task-specific heads and a shared representation. And now the shared representation is just a matrix as well, right? So the FIs are tall matrices and the phi star is a shared wide matrix. Each of these pre-training experts are going to generate a data set. We're going to collect these together as our pre-training data set. Feed this through an optimization problem, in this case, just least squares. It'll be a bilinear least squares to learn the shared representation. It will output a shared representation that's trained on this entire pre-training data set. Next, we'll be given a set of data from a new target task sharing the same structure, but a different specific head. This will generate a target task data set, which will then feed into a fine-tuning step. Now, what I want to quickly tell you about are the statistical advantages that we can get from this process, although that won't be the focus of this part of the talk. So in this context, if I have this policy computed on the right, then under suitable data coverage and task alignment conditions, we can provide the following bound on our excess risk. And just to remind you as to how to interpret this, this is the structure of our target task. And we have the assumption that the pre-training data set is much larger than the target data set. So this term in blue here is saying that when I'm learning my shared representation phi star, which has rough complexity k times dx, I get to divide this by all of the data that I use during pre-training. So the complicated feature is learned by pulling all of my data. And then the fine-tuning target, the fine-tuning component is, even though I only have access to my target data set, it's a much simpler thing to learn. And then using the very similar machinery to what we discussed in the previous part of the talk, we can translate this excess risk, or you can think of it as imitation loss, to a performance gap between the target task and the true optimal solution. And this, again, enjoys the same types of statistical benefits. So the main takeaway here is that representation learning, if done properly, reduces the complexity of learning new tasks by leveraging the pre-training data set. The question that I would like to address in my final part of the talk is, can we actually efficiently compute these features? Right? Even in this stylized linear setting, learning the shared representation is a non-convex problem. Right? You have this bilinear term between the task heads and the shared representation. Now, let me tell you what the traditional approach is to solving this problem in the context of data not generated by a dynamical system. And it's this idea of alternating descent, which allows for distributed learning of shared representations. I'm going to take my pre-training data set and kind of lay it out on the left. This algorithm proceeds in alternating steps, where on the one hand, I freeze my shared representation and update my task head. And on the other hand, I freeze my task head and update my shared representation. So for example, in task one, what would happen is, given some current estimate of the shared representation, I'll just solve this least squares problem to update my task head. And then to come up with a local update to the shared representation, I'll just take a gradient step with respect to this shared representation, assuming a frozen task head. And now I do this at every one of my different tasks. I want to emphasize on the left, the shared representation is frozen, so it's just a least squares problem. Then once I've taken these gradient steps on the right, I pull them together and average them. Modulo a normalization step, which I'm just hiding here for clarity, we can provide the following guarantee. This is not my work. This is kind of well known in the literature, which is that for IID and isotropic data with no label noise, my alternating descent procedure that I just showed you gives you results that enjoy these empirical risk minimizer rates that I showed you earlier. Now, the challenge is that data generated by dynamical systems is non-IID, anisotropic, and noisy. So I want to show you what can go wrong. In a very simple setting where there isn't even any dynamics here, it's just a linear representation learning problem. And the idea here is that, and there also is no covariate shift between training and test time. The only thing that we're going to tune is the degree of anisotropy in our data statistics. So as beta gets bigger, the covariance matrix of my data gets more and more stretched out. Now, if I run the alternating descent algorithm when beta is equal to 0 with isotropic data, life is good. I'm plotting here the subspace distance relative to the number of iterations. But as soon as I start introducing some anisotropy, this thing kind of fails catastrophically. Right? It turns out that the conditions for convergence really do rely on this isotropic assumption. Now, in this context, there's a very simple fix. I can just whiten my data. Right? If I whiten my data with the shared statistical structure, alternating descent works, and it just learns this modified shared representation. So let's see why we can't actually do this in the case of data generated by a dynamical system. So let's consider an idealized setting where for all of my tasks, my initial conditions, my initial state is drawn from the same isotropic Gaussian. Now I'm going to feed this initial condition through the closed loop induced by my different experts. This will generate a new steady state distribution for each of these different systems. And in particular, each of these different systems, each of these different tasks will twist and stretch the covariance matrix in its own unique way. So this means I can't whiten my data, because if I were to whiten my data, it would destroy the shared representation. The prefactor needed to whiten the red task is different from the prefactor needed to whiten the green task or the cyan task. So I can't just whiten my data naively. Thomas made this really beautiful observation, which is that if I rather do a local whitening of my gradient updates, then good things happen. So just to dive into the details a little bit, if I unpack what the gradient step looks like, I end up with a term that looks kind of as you would expect. And then I have a term on the right that is exactly kind of the empirical covariance of my task states. Now, if I modify the gradient rather than the data, then by the inverse of this covariance matrix, so you can think of this as correcting for the input anisotropy in the gradient step, then what we actually recover are in expectation the gradient steps that I would get had I had isotropic covariance. And so the convergence guarantees that I showed you previously should apply. And indeed, we showed that this is the case, and that for suitably tuned step sizes, we're able to show linear convergence of the subspace distance. However, there's some limiting factor here, which is we're limited by some conditioning number related to task coverage. So I'm going to come back to that question briefly in a little bit, but what I would like to just show you is what happens if we apply our approach to this setting that I showed you earlier. So if we use this debias and feature whiten method that I introduced previously, I showed you the feature whitening step. I didn't show you the debiasing step because it's kind of standard in the literature. You see that we get good behavior across all degrees of beta, kind of controlling this anisotropy. Now, this is a little bit of a toy example because we could have just whitened the data ahead of time and it would have worked. So let's take a look at what happens on a linear imitation learning with LQR experts problem, like I showed you earlier. And the thing that I want to emphasize here is each of the different tasks has their own data statistic geometry. If I apply alternating descent, then I get stuck, and I never converge to the appropriate feature space. Whereas if I apply our method, then we indeed do converge. And what we're also showing you here is that if I have more pre-training tasks, I do better. Also want to emphasize that if you take the data statistics into account properly, even with a single task using our method, that's the blue curve, we outperform a naive approach with 25 pre-training tasks. That's the green curve. Okay, now I know that I'm just about out of time. If I just want to take a couple minutes to connect these ideas to some recent methods in deep learning optimization. So our key idea here was to whiten locally using these gradient updates. Another way of thinking about this is this is a gradient preconditioner. It turns out you can connect this to a more general family of algorithms called Kronecker factored preconditioners, which are these pseudo second order methods that are gaining a lot of attention in the deep learning optimization community. A very brief kind of cartoon picture of how these things work is if I partition, say, my system, my neural network into a trunk and a linear head, I can define a left prefactor, which is essentially capturing the variability of the outputs to changes in features. And specialized to our linear representation setting, this just ends up being this kind of inner product of the task heads. And a right preconditioner, which captures the input anisotropy, which we've seen already. And so the proposed gradient update in this context is applying both a right and left prefactor or preconditioner. And if we look at what this looks like in the context of our algorithm, then we end up with the familiar right correction, but we also have this new term on the left, which in some sense captures the variability in terms of our tasks. Now, what does this buy us? Now, in the previous setting with just the right preconditioner, we were able to establish linear convergence, but it was somehow condition number dependent. If we apply this more general algorithm, we're in fact able to show that we get a condition number free linear convergence. So we get really strong, really nice behavior. If you'll just allow me a couple of minutes to show you what this looks like in empirically, we test this algorithm on a linear representation learning problem where we have high anisotropy both in pre-training and target, and we have distribution shift. Now, if we first examine the validation training loss just on the pre-training data, you'll notice that all of these kind of standard state-of-the-art algorithms, things like ADAM or natural gradient descent, actually work really well, in addition to our methods of DFW and KFAC. What's interesting, though, is if you then shift and look at the behavior of these in terms of learning the right features, state-of-the-art algorithms like ADAM and natural gradient learn the wrong features despite doing well on the pre-training data, whereas our approaches are learning the correct features. The subspace distance is decreasing. And you'll notice that KFAC slightly outperforms DFW because of this additional prefactor. And then last but not least, if you then think about how this would affect transfer loss, because ADAM and natural gradient learned the wrong features, they don't generalize well to new tasks, whereas our approaches indeed do generalize well to new tasks. So I know that this was a little bit rushed at the end, but if there's one message that you take away from this is that low pre-training validation loss does not directly translate to efficient feature learning and consequently low transfer loss. And in fact, in the context of machine learning for physical systems, because of this very close tie between the statistics of the data that I see and the actual systems that I'm learning, I need to adapt my optimization algorithm to the data statistics to actually learn features properly. So if we zoom back out and think about how this connects to this large behavior model, what I wanted to try to convey here is this ability to quickly learn new tasks is related to whatever it is in terms of these different model parameterizations enabling efficient feature learning rather than low training loss in pre-training. Okay, so I realize this is a little bit of a whirlwind. Thank you for bearing with me, but what we've looked at today are how physical machine learning differs and should be taken advantage of at all steps of the robot learning pipeline. And what I want to just end with is kind of highlighting this idea that, even though I presented these two paths as being diverging from each other, ultimately, I think the real success here will be if both sides, the side that's looking to generate more data, and the side that tries to understand how we can do the most with our data, work together in synergistic fashion. So can we use, for example, insights from dynamics and control and their connections to learning to inform what kinds of data we should generate, be they in simulation or in practice? And we showed some examples of that today. So with that, I am certainly out of time. I will thank you very much, and I'd be very happy to take questions. What I have here is just a list of relevant papers to the different parts of the talk. And you can scan the QR code when you go to my Google Scholar, which has the most recent versions of all of these. Thank you.
Thank you, Nick. Very interesting. And let's see, I'm sure some of our people have questions now, or some of the attendees, right? So there are big applauses. Who is going ahead first with question?
Yeah, thanks, Nick, for the great presentation. I have a question regarding the open loop unstable systems.
Mm-hmm.
You said that you are trying to make the Jacobian small.
Yes.
So do you include it as part of the loss function? Is this a term in the loss function, or you are just adding noise to the expert policy?
Great question. So in previous work, we had this work called Taylor series imitation learning. In that context, we put the Jacobian term in the loss function directly. Now, this was a little bit of an unrealistic assumption because in most cases, it's pretty hard to get your hands on that. In this new result, what we show is you don't need to explicitly include it in the loss function. In fact, just noising your data and balancing the noise data with clean data allows you to guarantee an upper bound on this Jacobian term, even though it's not explicitly in the loss function. There wasn't time to go into the details in the talk today, but it relates to a very kind of beautiful, fine-grained analysis of the linearization of the system along expert trajectories and understanding how the interplay between compounding errors and excitation behaves in the controllable subspace locally.
Okay. And in Taylor series imitation learning, you also had the possibility of adding the Hessian error, not only the Jacobian error.
Yes.
So using this method, can you also make the Hessian small, or?
That's an interesting question. My guess is you probably can, but what's interesting here is we show you don't need to. And so maybe to just connect these two things together, in the Tassel work, we showed that if you had something that was exponentially incremental input to state stable, in fact, only matching the Jacobian was sufficient, and it relied on a similar type of smoothness algorithm. Now, in terms of matching the Hessian, my guess is a similar analysis might apply, although the complexity will kind of blow up exponentially as you go higher up the Taylor series chain. But this will only have to happen if you don't have this kind of local linear stability that the exponential ISS gives you. Does that make sense?
Yeah. Okay, yeah, thank you very much.
Thanks.
More questions?
Hi, Nick. Thank you for the nice presentation. I have a question on the first part of the talk when it was assumed like the open loop and closed loop both are stable.
Yep.
So essentially, when we are doing this this action chunking, you said that there was this theoretical construct that was used to prove the results. How would you? My question is how can you spend some more time on that? Like what is it doing? Is it because you mentioned that it's no longer a feedback policy, but it initially is.
Yeah, absolutely. Yeah. So let me try to explain this in a way, and interrupt me if this isn't making sense. So essentially, what we need is for the policy pi hat to behave in a way that in the same way that it would if it were in closed loop with a system that was C-row stable, right? And so basically what this means is we really need this property here. I don't know if you can see my mouse, the kind of this decay property here to hold in the context of, this is specialized to regulating to the origin, but this is basically what you need to hold. Turns out this construct here is just a very convenient way of talking about it. But it's, there are other ways of any way that you could kind of enforce this exponential decay in magnitude, right? The idea here is my system is stable, so the state is decaying away exponentially. And so through smoothness, this means that my control action should also be decaying away exponentially in magnitude. So that's kind of the idea. And then the other idea here is that we are measuring state X and then playing something in open loop for L actions, right? So another way of thinking about this is a time varying signal for those L time steps, right? And so if you think about this from a kind of feed forward, feedback perspective, what this policy is doing over that window is providing a feed forward term that then your underlying stable system is tracking, right? If you think about the behavior of a incrementally stable system, if you don't touch it, it'll just converge to the origin. But if you provide it with a forcing function, it'll start tracking it. So that's what we're trying to do here.
Yeah.
Right?
Yeah, I got it. Yeah, I got the intuition now. Yes, thank you.
Yeah,
I
absolutely.
understood what's going on.
Yeah, so I mean, like this, this when we first kind of understood that this was the case, it was extremely non-intuitive, and it took me kind of a little bit of a while to kind of understand from a more controls perspective what was going on. But I really think this perspective of, for an open loop stable system, what you need to learn when you're doing imitation learning is not a feedback controller, but rather a reference trajectory generator in some sense. That's not quite true, but that's kind of the idea.
Yeah, sounds good. Thank you.
More questions?
Yeah, I just have one, just a quick question. From what I observed of this L chunk, and from the demonstration in slide 20 and some illustration in 18,
Mhm.
that although it's not specified, is it concave in the performance? Like,
Yeah,
find a sweet spot without experimenting?
that's a great question. So our analysis does not yet provide kind of a sweet spot type perspective. And the reason for that is we don't actually consider the statistical difficulties of learning a policy with, let's say, an L chunk window, right? And so in theory, we're assuming that our expert policy is realizable, which means that any L chunk policy is also realizable. So in theory, I can make this prediction horizon, I can make this chunk window as long as I'd like, and it'll kind of plateau out at the optimal behavior.
Yeah.
In practice, what we're seeing is that for longer chunk windows L, you essentially need more data to learn this whole thing properly. When we're doing this in practice, we're not doing these virtual dynamics. We're just parameterizing it as a chunk. And we're just kind of letting the data force it to behave in the way that it should. And so I think there is an interesting kind of trade-off here where there will be a sweet spot that balances stability, right? There's a minimum threshold that we need to go above, and the statistical complexity of learning a good model over that entire chunk.
Okay.
So that's
Right.
kind of where this trade-off curve, I think, is coming from.
Okay, thanks. That explains it a lot.
Yeah, great question.
Hi, Nick. Just one, sorry, Nara, just one quick comment, just mentioning this gradient learning, Nick, without using the data of the gradient, and it is providing a bound also on the quality of the learning, right? If I got that correct.
Yes.
So it's just a comment more than a question. This is very impressive and very relevant already to many other places. Also, for example, robust adaptive control, where if we are using learned components, we want to know their growth bounds. And this is now providing a method how to set up this learning when we don't have the data for learning the gradient. I'm very interested. So it's the paper on archive, right? Your latest, one of the latest.
So we had a version of this on archive. We took it down because we were going to completely rewrote it. The new version, which is really pretty, should be up very soon.
Perfect. Okay. Thank you so much. This is really impressive.
Of course. Thanks for bringing up the robust adaptive control perspective on this. Something that I didn't talk about is Thomas did this really beautiful fine-grained analysis that looks at kind of the interplay between the directions that you can excite with your noise and the directions where your error can actually hurt you. And it turns out these align with each other perfectly. And so you don't actually need local notions of persistence of excitation. You don't need exact parameter recovery. You can refine this whole thing to be projected onto a local controllable subspace only of sufficient magnitude to actually affect your error. So there's some really beautiful control theoretic insights underneath the hood here that I think are also very applicable to kind of robust adaptive control perspectives.
Excellent. And we'll explore more as we do with our ongoing work with this TASL and adaptive control. Thank you so much.
Thank you.
We'll share the paper soon, right? It's coming up together and we are all out of time. Thank you everyone for great questions. If more questions, just email Nick. I'm just apologizing because I'm in a rush now.
No
That's
worries.
why.
Thank you.
So,
Thank you
right,
so
if
much,
there are any
everybody.
questions, right, email Nick. Nick, thank you very much for taking the time. And we'll be soon in touch regarding the paper.
Sounds great. Thanks, everybody.
Please email the slides, right? Thanks. Bye-bye.
Thank you.
Thank you, Nick.